A natural gas power plant appears to own one of the cleanest business models in American industry. Gas enters through a pipe, electricity leaves through a wire. The owner buys one commodity, sells another, and keeps the difference. A billion-dollar asset that can look suspiciously similar to a very large lemonade stand. Natural gas supplied about 41% of utility-scale electricity in the United States during 2025, placing these plants near the center of the power system. Many can respond to changing demand, operate for long periods, and generate electricity without waiting for sunshine, wind, or a particularly cooperative forecast. So the owner fantasy writes itself. Buy cheap American gas, run an efficient turbine, sell power when prices rise, and collect the spark spread. But the spark spread is only the first line of the story, because the plant does not necessarily buy gas at the national benchmark price. It buys fuel delivered to one specific location, through one specific pipeline, under one transportation agreement with its own cost, firmness, and constraints. The plant may not receive the electricity price shown in a headline. Congestion, losses, timing, contracts, and settlement rules can change its realized value. Then the owner pays labor, maintenance, insurance, permits, water, chemicals, pipeline reservation, property tax, market administration, cybersecurity, and eventual equipment replacement costs. After operating costs come debt service, sustaining capital, major overhauls, working capital, collateral, taxes, and restricted reserves that can hold cash inside the project. Revenue can be strong while distributions remain weak. The turbine can be available while fuel is not. Electricity prices can rise while gas rises faster. A plant can generate every megawatt hour exactly as designed and still deliver almost no owner cash after funding the obligations surrounding the machine. That is the central paradox. The owner is not paid merely for possessing equipment capable of making electricity whenever the grid requests it. Owner cash appears only when fuel access, conversion efficiency, market position, availability, environmental compliance, maintenance discipline, contracts, and capital structure work together. This documentary follows that chain from the first investment dollar to the final distributable dollar, asking whether the plant can also fund its own future. Imagine purchasing a natural gas plant and receiving only the turbine. You would own remarkable machinery, but almost none of the business required to operate it. The complete ownership unit begins with land, access roads, drainage, security, fire protection, maintenance space, and legal control of an industrial site. That site must connect to a gas pipeline on one side and the electric grid on the other, with a complete operating system between them. A combined cycle plant includes gas receiving, a combustion turbine, generator, heat recovery steam generator, steam turbine, condenser, cooling equipment, water treatment, and emissions controls. Control rooms, transformers, switch yards, warehouses, spare parts, digital systems, and trained workers complete the physical asset that must remain available and compliant. But the contractual plant can be just as valuable as the physical plant, because machinery cannot create revenue without enforceable rights and dependable services. The owner may need gas supply, firm pipeline transportation, grid interconnection, water access, wastewater arrangements, land easements, insurance, and transferable operating authorizations. Revenue can depend on a power purchase agreement, tolling contract, capacity qualification, market registration, or regulated recovery, with each structure allocating risk differently. Some contracts create revenue, others preserve the right to operate. The rest mainly determine who receives the invoice when reality becomes unexpectedly expensive. An acquisition can also transfer deferred maintenance, future inspections, catalyst replacement, environmental obligations, network upgrade payments, collateral requirements, property taxes, and decommissioning costs. A low purchase price may represent a genuine bargain, or a carefully wrapped collection of future capital bills that the seller no longer intends to fund. Our due diligence must therefore extend beyond recent revenue and operating hours to component life, fuel access, permits, contracts, grid position, and post-closing capital. The plant's value lives in the relationship between equipment, contracts, rights, and obligations, not inside the combustion turbine or generator considered alone. A strong machine with weak fuel access can be stranded. A good site with poor interconnection economics can be trapped. Reliable revenue with unreliable equipment can become penalties. The owner buys a complete system, valuable only when every essential part remains legally available, technically capable, commercially connected, and financially funded. The phrase natural gas power plant hides several different businesses, each with its own equipment, operating role, revenue logic, fuel exposure, and maintenance burden. A simple cycle plant burns gas in a combustion turbine and turns a generator directly, producing electricity without adding a separate steam cycle. Its advantage is flexibility and relatively fast response. Its disadvantage is usually higher fuel consumption for each megawatt hour than a modern combined cycle plant. A combined cycle plant captures hot turbine exhaust inside a heat recovery steam generator, producing steam that drives a second turbine and creates additional electricity. That recovered heat improves efficiency, but it also adds steam equipment, cooling systems, water treatment, operating interfaces, and additional future maintenance obligations. Aeroderivative turbines can emphasize rapid starts and flexible operation, making them useful when the grid values responsiveness more than sustained fuel efficiency. Industrial frame turbines may favor scale and sustained output, while reciprocating engines offer modular capacity, fast starts, and a different pattern of maintenance and redundancy. Combined heat and power can add steam revenue, but one industrial customer also creates delivery obligations, contract concentration, and another source of operational dependence. Our hero asset is a utility-scale combined cycle plant, large enough that fuel economics, grid access, major maintenance, and financing cannot be treated as footnotes. Combined cycle units often serve sustained or intermediate generation, operating when their variable cost remains competitive and adjusting output as demand and market conditions change. A peaking plant may run far fewer hours, yet earn meaningful value from readiness, rapid response, reserves, or operation during a limited number of scarcity periods. That means efficiency alone does not determine investment quality. The plant must convert its technical advantages into revenue under the rules of its specific market. An efficient plant behind transmission congestion may realize weak prices, while a less efficient plant with valuable location and dependable capacity payments may produce steadier cash. The best turbine on paper is not automatically the best business. Value appears when physical capability, commercial structure, and market role reinforce one another. Before the first megawatt reaches the grid, the owner must fund a long procession of development, construction, connection, and reserve items that produce no revenue. EIA's 2026 modeling assumptions include a reference single-shaft combined cycle plant rated at 627 megawatts, with an overnight capital cost of $1,086 per kilowatt. Multiplying those reference inputs produces roughly $681 million, a useful, standardized construction estimate for an illustrative plant measured in $2025. But overnight cost is not total funded capital because it treats the project as though construction appeared instantly without financing time or development uncertainty. Real projects experience time through engineering, permits, procurement, construction schedules, equipment delivery, testing, and months when invested capital earns no operating revenue. The budget can include land, site preparation, gas interconnection, switchyard construction, transmission upgrades, owner's engineering, and infrastructure beyond the central generating equipment. It can also include initial spare parts, construction insurance, contingency, interest during construction, and professional costs required to move the project toward commercial operation. Before opening, lenders and counterparties may require working capital, hedge collateral, a debt service reserve, and dedicated funding for future major maintenance cycles. Regional labor, ambient conditions, road access, water availability, pipeline distance, and transmission requirements can move the project far from a national reference estimate. For explanation, this plant can be modeled at $780 million to $920 million of total funded capital, but that range is not a project quotation. Greenfield development carries permitting, construction, schedule, turbine delivery, gas connection, and interconnection risk before the asset has an operating history or dependable cash flow. Buying an operating plant removes some development uncertainty, but replaces it with equipment condition, contract renewal, merchant exposure, and near-term capital work risk. Repowering may reuse land, grid access, or supporting infrastructure. Yet integration work and new environmental, construction, and financing obligations can remain substantial. Debt reduces the initial equity requirement, but scheduled payments continue when spreads weaken. Equity absorbs overruns, volatility, reserve needs, and delayed distributions. Purchase price is only one doorway into ownership. Total capital must also fund closing, liquidity, repairs, future maintenance, and every obligation needed to keep operating. A natural gas plant can be paid for several different products, and confusing those products is one of the fastest ways to misunderstand the business. The first product is energy, net megawatt hours sold through a contract, regulated framework, or wholesale market settlement after the plant actually generates electricity. In organized markets, energy may be scheduled day ahead and adjusted in real time, so dispatch changes can alter both output and final settlement value. The price received by the plant may differ from a regional headline because electricity moves through a constrained network with local congestion and transmission losses. The second product is capacity or resource adequacy, payment for dependable future availability, not payment for electricity that the plant has already produced. Capacity markets operate in some regions, not across the entire United States, and qualification, performance requirements, delivery periods, and penalties vary by market. The third product is ancillary services, which can compensate qualified plants for reserves, regulation, voltage support, or other short-duration functions that stabilize the grid. The fourth category is contracted payment, including power purchase agreements, tolling arrangements, regulated recovery, or public power structures built around different ownership objectives. Each commercial structure allocates risk differently, ultimately determining who carries fuel prices, controls dispatch, absorbs congestion, funds outages, and faces performance obligations. A merchant owner may retain more upside when power prices rise, but also carries greater exposure when gas costs increase or profitable dispatch declines. A tolling arrangement can reduce commodity exposure by shifting fuel or dispatch responsibility, while the plant owner remains accountable for availability and technical performance. Capacity revenue can help recover fixed costs, yet failure during a critical period may reduce payments, trigger penalties, or weaken future qualification. Even multiple revenue streams can hide weak economics when energy revenue meets expensive gas, ancillary operation adds wear, or contracts approach expiration. The owner must ask who supplies fuel, who controls starts, who absorbs congestion, who funds outages, who posts collateral, and who pays performance damages. Revenue is the visible side of the market relationship. Risk allocation is the side that determines whether those payments become durable owner cash. Natural gas prices are often discussed as though every power plant opens the same national menu and orders fuel at one identical number. It does not. A benchmark such as Henry Hub is useful, but the plant pays for natural gas delivered to its own gate. Delivered costs can include the commodity, geographic basis, pipeline transportation, reservation charges, balancing, fuel retention, taxes, compression, and scarcity premiums at the plant gate. Location changes the business because gas demand from heating, industry, exports, and power generation can compete for limited pipeline capacity near the site. During ordinary conditions, a difficult location may look manageable. During extreme conditions, the delivered price difference can become the entire investment case for the owner. Transportation contracts matter because fuel availability has option value, especially when the power market rewards plants that can operate during stress conditions. Firm transportation usually requires a reservation payment, whether the plant runs or not, creating a fixed cost that can look inefficient during quiet months. But when pipelines are constrained, firm rights may preserve the ability to operate during the hours when electricity becomes most valuable for the owner. Interruptible transportation can reduce fixed commitments, but it may leave the plant without fuel precisely when the grid and market need it most. Cheap access that disappears during scarcity is not the same economic product as dependable access that survives a stressed pipeline system under pressure. The owner must also manage gas nominations and balancing because pipeline schedules are established before electricity dispatch is fully known by the market operator. If real-time dispatch changes after fuel is nominated, the plant may burn more or less than scheduled and incur imbalance charges or operational constraints. Fuel pressure matters too. The turbine requires gas within technical specifications, so compressor conditions and lateral design can limit expected plant output. Gas price therefore means three separate questions: the commodity benchmark, transportation cost, and whether the fuel can physically arrive when required at required pressure. A small, delivered price difference can reshape annual fuel expense across millions of megawatt hours, making fuel strategy part of design, contracts, and liquidity. The operational chain begins at the gas receiving station, where fuel is metered, pressure regulated, filtered, conditioned, and directed toward the combustion turbine. Inside the turbine, a compressor draws in air and raises its pressure before natural gas mixes with that air and burns inside the combustion system. The resulting high-temperature gas expands through turbine blades, turning a shaft connected to a generator and converting fuel energy into the first stream of electricity. In a combined cycle plant, hot exhaust does not simply leave the stack. It enters the heat recovery steam generator and transfers remaining energy into water. That recovered heat creates steam, which drives the steam turbine and produces additional electricity without requiring a second full stream of natural gas. Afterward, the condenser removes heat from the steam, while cooling towers or air-cooled equipment return water or working fluid toward another operating cycle. Pumps, fans, compressors, cooling systems, water treatment, emissions controls, lighting, and digital equipment consume part of the electricity generated inside the plant. Gross generation minus this internal consumption becomes net generation, the output actually available for sale, even though fuel supported the complete operating system. The control room coordinates starts, ramps, temperatures, vibration, emissions, water chemistry, and grid instructions while operators protect equipment, reliability, and market commitments. Owners must decide not only whether the plant can run, but whether running under current prices and equipment conditions creates enough economic value. Each start consumes fuel before stable output, while repeated heating and cooling create thermal stress that can accelerate future maintenance obligations and costs. Owners therefore manage both operating hours and starts, because two plants with similar annual generation can accumulate very different patterns of component wear. Availability also has timing value. Losing a low-price hour is inconvenient, while losing a scarcity hour can damage energy, capacity, and contract revenue together. Dispatchability depends on fuel, equipment condition, permits, staffing, ambient conditions, and grid instructions aligning at the same moment, not merely on turbine design. The molecule-to-megawatt process is impressive, but every stage either creates margin or claims part of it before the owner can value one net megawatt hour. The most important operating number in a natural gas plant is often heat rate, measuring how much fuel energy the facility needs to produce electricity. For the EIA reference combined cycle plant, the modeled heat rate is 6,226 British thermal units for each kilowatt hour of modeled electrical production. For financial analysis, that becomes 6.226 million British thermal units per megawatt hour, creating a direct bridge between plant efficiency and delivered fuel cost. The core fuel cost formula is simple: heat rate multiplied by delivered natural gas price, using the plant's actual net performance rather than a brochure assumption. At $4 per million British thermal units, the reference heat rate produces a simplified fuel cost of about $24.90 per megawatt hour. Adding the reference variable operating and maintenance input of $3.49 raises the simplified variable cost to approximately $28.39. That figure is not a final dispatch bid, and certainly not owner break-even, because starts, imbalances, consumables, market fees, and incremental maintenance remain outside it. The apparent spark spread subtracts fuel from electricity value. Contribution margin is stricter, subtracting the complete variable cost of producing one net megawatt hour. At this reference heat rate, every $1 increase in delivered gas price raises fuel cost by approximately $6.23 per megawatt hour. Across more than 3 million annual megawatt hours, that $1 fuel change can shift yearly expense by roughly $20 million before other operating effects. Efficiency also changes with reality. Hot weather, equipment degradation, part load operation, fouling, and higher auxiliary demand can consume the advantage assumed in the model. Frequent starts add fuel before stable output and create maintenance wear, meaning two plants with similar annual generation can still have different variable economics. Dispatch break-even asks whether the next megawatt hour covers fuel and variable costs. Plant operating break-even adds labor, insurance, compliance, maintenance, and fixed transportation. Debt service break-even adds scheduled principal and interest, while owner cash break-even also funds sustaining capital, major maintenance, working capital, collateral, taxes, and reserves. A megawatt hour can carry positive contribution margin, while the full asset produces weak owner cash, because operating efficiency cannot erase an overburdened capital structure. Fuel expense rises and falls with generation, but many costs continue whether the plant operates at full output, cycles occasionally, or waits for dispatch. A utility-scale plant still needs trained operators, technicians, engineers, managers, compliance staff, security, digital systems, and emergency capability even throughout low-output periods. The owner also pays insurance, property tax, land obligations, fixed pipeline reservation, market registration, metering, environmental testing, cybersecurity, spare parts, and routine maintenance. A long-term service agreement may include fixed payments, variable charges, inspection milestones, covered components, exclusions, and detailed rules governing how maintenance risk is shared. EIA's reference model assigns fixed operations and maintenance of $16.23 per kilowatt year to its illustrative combined cycle technology for planning. Applied to 627 megawatts, that modeling input equals slightly more than $10 million annually before many site-specific owner expenses are included. It does not automatically include every insurance premium, property tax bill, corporate allocation, fixed fuel reservation, major overhaul, sustaining capital project, or reserve requirement. This creates operating leverage. When generation rises, fixed costs spread across more megawatt hours. When dispatch falls, the same annual burden remains unchanged. As output declines, fixed cost per produced megawatt hour increases precisely when energy margin may already be weakening, tightening the plant's economics from both directions. Major maintenance adds another problem because turbines, generators, heat recovery systems, transformers, cooling equipment, and emissions controls do not wear according to smooth monthly invoices. They create inspection cycles, planned outages, component replacements, specialist labor, and occasional discoveries that concentrate several years of economic consequences into one maintenance period. A quiet maintenance year can make cash flow look unusually strong, while a major inspection year makes the same underlying plant appear dramatically weaker. Reserves reduce distributions today so future work can be funded. Refusing to build them improves current owner cash by converting maintenance into a later liability. A low capacity factor is not automatically bad when fixed revenue supports readiness, and a high capacity factor is not automatically good at weak margins. The ownership objective is not maximum operating hours. It is durable, risk-adjusted cash after funding readiness, maintenance capability, future repairs, and the full fixed cost machine. Power plant discussions often stop at EBITDA, but owners cannot distribute EBITDA because that measure sits above debt service, capital spending, reserves, collateral, and taxes. Revenue first pays for delivered gas and other variable operating costs, leaving contribution margin rather than profit, free cash flow, or money available to equity. From contribution margin, the project must cover labor, insurance, compliance, fixed transportation, routine maintenance, property costs, market administration, and corporate support overhead. What remains may resemble EBITDA-like operating cash, a useful performance measure that still ignores how the plant was financed and what equipment will require next. Two plants with identical operating cash can deliver different owner outcomes when one carries conservative debt and the other faces heavy scheduled principal and interest. Debt service arrives according to a contract, not according to whether power prices, dispatch volumes, gas basis, or maintenance timing were kind during that period. After debt, the plant still needs sustaining capital for pumps, controls, transformers, cooling equipment, cybersecurity, safety systems, and smaller projects that preserve capability. Major maintenance creates a second capital demand, requiring cash for inspections, component replacement, specialist labor, outage work, and discoveries made after equipment is open. Reserves convert future obligations into current funding needs, reducing today's distribution so tomorrow's overhaul does not depend entirely on emergency equity or new borrowing. Working capital and collateral can trap additional cash when fuel purchases, market settlements, hedges, or performance guarantees require funding before corresponding revenue is collected. Taxes, insurance adjustments, environmental obligations, and contractual true-ups can further separate accounting performance from the cash legally and practically available for distribution. Lenders may also restrict distributions through covenants, reserve tests, or minimum liquidity requirements, meaning cash can exist inside the project while remaining unavailable to owners. Timing matters. A strong operating quarter may coincide with debt payments, outage invoices, collateral calls, and reserve deposits, producing little or no distributable cash. The owner cash bridge therefore runs from revenue to variable costs, fixed costs, debt service, capital spending, reserves, working capital, collateral, taxes, and finally, distributions. EBITDA can describe the engine's operating performance, but owner cash reveals whether the complete capital structure, maintenance plan, and risk system can actually support ownership. Hidden margin rarely appears as one dramatic line item. It accumulates through dozens of small decisions that improve fuel conversion, availability, market realization, and maintenance timing. A modest heat rate advantage saves fuel on every megawatt hour, so disciplined tuning, clean equipment, and timely repairs can create recurring value across millions of annual units. Reducing auxiliary load increases net electricity available for sale without increasing gross generation, allowing pumps, fans, cooling systems, and controls to become economic assets. Dependable fuel access creates margin when constrained competitors cannot run, because firm transportation and strong gas operations preserve dispatch during the market's most valuable hours. Start decisions also matter. Avoiding unnecessary starts reduces startup fuel, thermal wear, and future maintenance consumption, while preserving flexibility for periods with stronger economics. Availability is most valuable when timed correctly, so preventing one outage during a scarcity period can matter more than improving average annual availability by several ordinary hours. Maintenance planning creates hidden margin through accurate inspections, critical spares, specialist scheduling, and shorter outages that return the plant to service before valuable market windows close. Long-term service agreements can preserve or destroy value depending on covered components, exclusions, escalation rules, outage support, parts logistics, and the incentives assigned to each party. Commercial operations add another layer by coordinating fuel nominations, dispatch bids, hedges, and settlement review, so technical performance becomes realized revenue instead of accounting leakage. Interconnection rights, capacity qualification, environmental permits, and pipeline agreements can quietly protect revenue because losing any one may reduce output, products, or operating flexibility. Working capital discipline creates value by funding fuel, collateral, and repairs without forcing emergency borrowing or missed opportunities when market conditions become briefly attractive. Accurate metering, invoice review, contract administration, and market settlement can recover small recurring amounts that disappear when operational data and commercial records are poorly reconciled. Across more than 3 million annual megawatt hours, even $1 of improvement per unit can add roughly $3 million before financing, taxes, and capital spending. These advantages reinforce one another. Better efficiency improves dispatch. Better dispatch supports maintenance funding, and better maintenance protects the availability needed to capture high-value revenue. The hidden margin is not a heroic commodity forecast. It is a repeatable operating system that converts small technical, contractual, and financial advantages into durable owner cash. Behind the turbine sits a liability schedule, inspections, permits, contracts, reserves, and end-of-life obligations that continue long after the purchase agreement is signed. Combustion turbines and generators consume service life through operating hours, starts, temperatures, and vibration, eventually requiring inspections, specialist labor, and expensive component replacement. The steam cycle can hide separate exposure inside heat recovery tubes, drums, valves, piping, condensers, and chemistry systems whose condition is less visible than turbine output. Environmental compliance depends on permits, emissions monitoring, catalysts, testing, reporting, and operating limits. A compliant plant today still carries future replacement and renewal work. Water access creates another ownership obligation because treatment systems, withdrawal rights, discharge requirements, chemistry control, and cooling performance must remain available together. Interconnection rights are valuable, but protection equipment, metering, transformers, reactive power capability, and assigned network work can create continuing technical and financial responsibilities. Fuel agreements may include reservation charges, balancing duties, pressure requirements, credit support, and minimum commitments that remain costly even when dispatch falls. Capacity commitments and commercial guarantees can convert an outage into reduced payments, penalties, replacement costs, or weaken qualification during later delivery periods. Insurance transfers selected risks, not every risk. Deductibles, exclusions, coverage limits, market repricing, and claims disputes can leave substantial losses with the owner. Property taxes and local obligations can change through reassessment, jurisdictional rules, site improvements, or expiring agreements, creating costs unrelated to electricity production. Collateral and liquidity requirements can expand precisely when commodity prices, volatility, or counterparty concerns rise, trapping cash while operating conditions are already difficult. Digital controls, communications, and cybersecurity systems require continuous maintenance, access discipline, software support, and replacement over time before technical obsolescence threatens reliable operation. Eventually, retirement requires decommissioning, equipment removal, environmental closure, site restoration, contract termination, and funding that may receive little attention during profitable years. These liabilities interact. Weak cash can defer maintenance, deferred work can reduce availability, lower availability can trigger penalties, and penalties can further weaken cash. Good ownership therefore identifies each obligation, assigns responsibility, estimates timing, and funds the required reserve before the turbine turns a manageable liability into an owner trap. The owner trap begins when a plant appears operationally sound, yet its contracts, debt, fuel access, maintenance needs, and liquidity cannot survive the same downside. A buyer may underwrite recent earnings while ignoring expiring contracts, deferred repairs, rising basis, collateral needs, and the next major outage already approaching. The failure engine often starts with higher delivered gas cost, which raises variable expense and removes profitable dispatch hours from the plant's operating schedule. Fewer profitable hours mean less contribution margin, even though labor, insurance, fixed transportation, compliance, property costs, and debt obligations continue almost unchanged. As fixed obligations consume a larger share of cash, management may draw reserves or delay discretionary work to preserve near-term liquidity and scheduled payments. Reserve withdrawals can solve an immediate cash problem, but they also remove the funding intended for inspections, component replacement, collateral, or a future outage. When maintenance is deferred, equipment condition can deteriorate, heat rate may weaken, startup reliability can fall, and small defects can become expensive planned work. Lower availability then reduces the plant's ability to capture valuable hours, fulfill contracts, qualify for capacity payments, and avoid future performance penalties. Missing high-value periods weakens cash further, creating another reason to defer maintenance, reduce reserves, or postpone repairs that protect future operating capability. Eventually, the project may require emergency equity, expensive refinancing, covenant relief, an asset sale, or restructuring merely to restore liquidity and complete necessary work. The warning signs usually appear before failure: shrinking reserves, repeated outage extensions, rising forced outage rates, expiring contracts, weak collateral headroom, and postponed inspections. Leverage accelerates the mechanism because debt payments remain scheduled, while merchant revenue, fuel basis, maintenance discoveries, and collateral demands move unpredictably over time. An owner with patient capital and operating depth may absorb the cycle, while a thinly capitalized owner can turn temporary stress into permanent impairment. Breaking the engine requires early action. Protect liquidity, fund maintenance, renegotiate risk allocation, reduce leverage, improve fuel access, or sell before options disappear. The owner trap is therefore not one catastrophic event. It is a reinforcing system where weakening cash, maintenance, availability, and financing progressively reduce every exit. Scenario analysis becomes useful only when the same plant, capital structure, contracts, and maintenance obligations are tested against several coherent operating environments. Our 4 cases hold the complete asset constant, then change delivered gas cost, power market value, availability, collateral pressure, and the owner's financial resilience. In the balance case, delivered gas remains manageable, dispatch is ordinary, availability meets expectations, and recurring revenue covers operating costs, debt, reserves, and modest distributions. A conservative infrastructure owner fits this case by accepting moderate returns, maintaining liquidity, funding reserves, and avoiding leverage that depends on exceptional market conditions. In the favorable merchant case, power prices strengthen, gas access remains dependable, and high availability lets the plant capture more profitable hours and ancillary opportunities. An experienced merchant operator can convert that upside through disciplined bidding, fuel management, outage timing, and settlement control without treating a strong year as permanent. In the fuel stress case, regional basis rises, transportation tightens, and profitable dispatch falls while fixed operating costs, debt service, and maintenance obligations continue. A strategic utility or diversified portfolio owner may withstand this pressure by valuing reliability, customer obligations, and portfolio balance beyond the plant's standalone merchant cash. In the compound shock case, weak margins coincide with a major outage, collateral calls, reserve depletion, and scheduled debt payments, compressing every source of liquidity. A thinly capitalized, leveraged owner is poorly matched to this case because temporary operating stress can quickly become covenant pressure, emergency financing, or forced sale. The turbine is identical across all four cases, yet owner outcomes differ because capital patience, commercial capability, portfolio context, and liquidity absorb risk differently. The contracted owner sacrifices some upside for predictability. The merchant operator accepts volatility. The strategic owner values system benefits. The leveraged owner depends on timing. Break-even also changes by owner. One measures contractual coverage, another merchant contribution, another portfolio reliability, and another the narrow cash remaining after debt. No scenario proves one owner type universally superior. The question is whether the owner's capital, expertise, obligations, and risk tolerance match the asset's exposures. Scenario analysis therefore leads to the final ownership question. Not whether a gas plant can make money, but which owner can carry its complete system. There is no universally best owner for a natural gas plant, because the asset's value depends on matching capital, operating skill, contracts, and risk tolerance. The correct owner must understand the physical plant, manage fuel and power markets, fund maintenance, honor contracts, and preserve liquidity through unfavorable operating periods. A regulated utility or public power owner may value reliability, customer obligations, and system planning beyond standalone merchant cash, provided recovery and governance remain appropriate. An infrastructure investor may fit a contracted plant when revenue is durable, leverage is conservative, reserves are funded, and operating responsibilities are clearly assigned. An experienced merchant operator may accept greater volatility when it possesses fuel expertise, market systems, outage discipline, settlement control, and enough liquidity to survive weak spreads. A highly leveraged financial buyer can succeed only when the downside is genuinely underwritten, improvement plans are executable, and refinancing is not the hidden operating strategy. An industrial owner may value combined heat and power when electricity, steam demand, site operations, and customer concentration fit the broader manufacturing economics. The first ownership test is fuel. Can the owner secure delivered gas, manage transportation rights, handle nominations, and withstand scarcity without losing critical dispatch? The second test is commercial capability. Can the owner value energy, capacity, ancillary services, contracts, congestion, settlements, and counterparty obligations together effectively? The third test is operational depth. Can the owner plan outages, retain skilled teams, manage service agreements, protect heat rate, and respond when equipment condition changes? The fourth test is capital resilience. Can the owner fund debt service, sustaining work, major maintenance, collateral, taxes, and reserves before distributions are considered? The fifth test is governance. Are decision rights, reporting, incentives, and escalation paths designed to resolve problems early rather than postpone them across organizational boundaries? Due diligence should therefore underwrite downside cash, maintenance timing, contract expiry, fuel stress, and liquidity needs instead of relying on recent EBITDA or a favorable forecast. A complete ownership decision joins four systems: physical capability, commercial structure, financial capacity, and the liability schedule that continues through operation and retirement. Owning a natural gas plant means owning the whole system. The best owner is the one able to operate, fund, and adapt it through changing cycles.